Okay, welcome back. Uh, in this lecture, I am going to talk about how to compute capacity of some very simple channels. So, I will start off with describing what is a discrete memoryless channel, and then I am going to talk about what is a uniformly dispersive channel and what is a uniformly focusing channel. And once I have described what is a uniformly dispersive channel and uniformly focusing channel, I will describe what is known as a strongly symmetric channel, a channel which is both uniformly dispersive and uniformly focusing is known as strongly symmetric channel, and we will compute the capacity of a strongly symmetric channel. After that, we are going to talk about what is a symmetric channel and how we can decompose a symmetric channel into strongly symmetric channel, and then we are going to talk about how to compute the capacity of a symmetric channel. So, let us start with the definition of a discrete memoryless channel. A discrete memoryless channel is specified by these three quantities. One is the input alphabet, I am calling it A, output alphabet B, and conditional probability distribution, probability of y given x. So, if it is a memoryless channel, then yn given previous inputs and previous output, it only depends on the current input. Now, we can similarly define what is a discrete memoryless channel without feedbacks. So, for a discrete memoryless channel without feedback, probability of xn given past values of x and past output does not depend on past output, it only depends on the past inputs. So, that is a discrete memoryless channel without feedback. For a discrete memoryless channel without feedback, we can write probability of y1, y2, y3, yn given x1, x2, xn in terms of product of these, probability of yi given xi. Proof is very straightforward. We can write this joint distribution of probability of x1, x2, x3, xn and y1, y2, yn in this particular fashion, right. And then we know this channel is discrete memoryless without feedback. So, probability of yi given x1, x2, xn, xi and y1, y2, yi minus 1 will be given by probability of yi given xi. This follows from the fact that this is a discrete memoryless channel without feedback, right. And then, so this is basically given by this, and now I can write this as probability of x1, x2, x3, xn, and if I divide both sides by that, here I will get probability of y1, y2, yn given x1, x2, xn, and the right hand side I will get this expression. Okay. So, for a discrete memoryless channel without feedback, probability of y1 given y2, yn given x1, x2, xn can be written as product of these probability of yi given xi. We define capacity of a discrete memoryless channel as the maximum average mutual information that can be conveyed by the choice of input distribution. So, this is, we are maximizing mutual, what is the input distribution that maximizes the mutual information between this input to the channel and the output to the channel, right. So, we are interested in computing this capacity. We are also interested in knowing what is the input distribution that will achieve this capacity. We can also write this in terms of, so from the definition of mutual information, I can write this as entropy of y minus entropy of y given x. So, I can write capacity expression in this form, right. Now, let us come to what is a uniformly dispersive channel. So, I have been given a discrete memoryless channel which has k inputs and j outputs. We say a discrete memoryless channel is uniformly dispersive. Probabilities of the j transitions leaving an input when put in decreasing order has same value no matter what input we consider. So, what we are saying is we are looking at dispersion from the input. So, looking at these probabilities. Okay. when we arrange these probabilities in the decreasing order, they have the same order no matter what input we consider. For example, if you look at this example, if we consider input 0, these transition probabilities when arranged in descending order is half and half. This is for the input 0, right? And if we consider input 1, again if we consider these transition probabilities in descending order, this is half and half. So, in this case my k is 2, j is 3. So, if you see, no matter whether I consider input 0 or input 1, if I arrange these transition probabilities of leaving that particular input, whether it is input 0 or input 1, when I arrange them in descending order, it is same. So, that means this is a uniformly dispersive channel. Now, is this a uniformly dispersive channel? So, what do we need to do? We look at the input. So, when we arrange these probabilities of these transitions of leaving this particular input, and if we arrange these transition probabilities in decreasing order, we will have 1 minus p and p. What about 1? Again, if we arrange them in descending order, this will be 1 minus p and p. So, it is same. So, this is also a uniformly dispersive channel. So, is it clear what is a uniformly dispersive channel? Okay. So, the claim I am making is, for a uniformly dispersive channel, independent of choice of input distribution, uncertainty in y given x is given by this, where p1, p2, pj are the transition probabilities of leaving each input. In channel capacity, we can write as mutual information, we can write as h of y minus h of y given x. What I am saying is, for a uniformly dispersive channel, irrespective of what your input distribution is, h of y given x is given by straightforward. If you look from a definition of uniformly dispersive channel, consider uncertainty of y given entropy of y given x as any input a k. This is given by this expression, and this does not depend on what a k is. Why? Because if you look at the transition probabilities, if you arrange them in descending order or ascending order, it is same no matter what your input is, right. So, from the definition of uniformly dispersive channel, we can write h of y given x as any input a k can be written like this. So, we know uncertainty of y given a particular input. So, if you want to find out uncertainty in y given x, that would be, you will multiply this uncertainty of y given x a k by the probability of a k, okay, and sum over all inputs. Now, this is independent of input k. So, that we can take it out, and this summation of a k, that will be 1. So, what you would get is this, fine. So, what we have shown is uncertainty in y given x for a uniformly dispersive channel is given by this expression, which is nothing but this. Okay. Now, let us write then the expression for channel capacity for a uniformly dispersive channel. We said it is the maximum of mutual information over all input distribution. So, that we can write as h of y minus h of y given x. H of y given x is given by this expression, and it is independent of input distribution p of x. So, then we can write the expression for channel capacity as, you find the input distribution that will maximize h of y plus this. Now, when will h of y be maximized? When y is uniformly distributed. So, we need an input distribution which would make y uniform. This proof we have already done. So, is it clear? Okay. So, this is the capacity of a uniformly dispersive channel. Now, let us look at what is a uniformly focusing channel. So, I have a discrete memoryless channel again with k inputs and j output. We say a discrete memoryless channel is uniformly focusing if the probabilities of the k transition to an output letter when put in decreasing order is same for all outputs. So, what we are doing is we are looking at the output and we are looking at all transitions that are basically terminating at this particular output, right. We look at the transition probabilities, we arrange them in the descending order. Now, if that is same for all the outputs, then that channel is known as uniformly focusing channel. So, let us look at this example. If we look at output B1, if we look at output V1, there are two transitions which are terminating at B1, and what is the probability? 1 by 2 and 1 by 4. So, if we write them in descending order, we will have 1 by 2 and 1 by 4. If we look at B2, there are again two transitions. What are the probabilities? Again, if we put them in decreasing order, it will be same. And same thing holds for B3 and B4. So, then this is a uniformly focusing channel. Now, let us go back to the previous example. Is this a uniformly focusing channel? No. Why? Because you can see in B1 it is only half, here it is half and this is half. So, this is not a uniformly focusing channel. Is this a uniformly dispersive channel? No. You can see if we consider input 0, the probabilities are half, 1 by 4, 1 by 4. But if we consider this particular input, it is half. So, these probabilities are not same. So, this is not a uniformly dispersive. So, this is a uniformly focusing channel, but it is not a uniformly dispersive channel. The earlier channel which we showed, it was uniformly dispersive, but it was not uniformly focusing. What about this? This was uniformly dispersive, we saw. Is it uniformly focusing? It is uniformly focusing. You can see basically if you consider this output 0, the probability is 1 minus p and p when arranged in descending order. Similarly, for 1, it is 1 minus p and p. So, this is both a uniformly focusing and dispersive channel. Okay. Now, for a uniformly focusing channel, this relation holds. For a k input j output uniformly focusing channel, it is the uniform input distribution which will result in uniform output distribution. So, let us prove this. And also the maximum value of h of y over all input distribution is given by log of j, where j is number of outputs. So, I can write p of y as p of y given x into p of x sum over all x. Now, if the input is uniformly distributed and I have k input, so p of x will be 1 by k. So, I will get this. Now, now what is this? Summation of p of y given x sum over all x's. So, you are looking at a particular y and you are summing up all these transitions which are terminating at your y coming from all x's, right. Now, if this is a uniformly focusing channel, we know that these transition probabilities when arranged in descending order is same. So, if you sum them up, they will be same no matter what my y is, correct. So, no matter what my y is, this will be same. So, for a uniformly focusing channel, the summation of P of y given x over all x, that will be a constant. So, P of y, what is the value of P of y? P of y will be 1 by j, right. So, since discrete memoryless channel is uniformly focusing, sum of the right hand side will be same for all j values of y. So, this P of y will be 1 by j, because when you add P of y over all y's, basically they sum up to 1. Okay. So, output is uniformly distributed, right. So, that is what we have proved, that if the input distribution is uniform, the output will be uniform for a uniformly focusing channel, and the maximum value of h of y is basically given by log of j, and it is basically the uniform input distribution that will result in that, right. Okay. So, any questions so far on what is a uniformly dispersive channel or what is a uniformly focusing channel? So, a channel which is both uniformly dispersive and focusing is known as strongly symmetric channel. So, this example that we saw, this is an example of a strongly symmetric channel. Now, can we write down the expression for capacity for a strongly symmetric channel? We know if it is uniformly dispersive, we know what is the value of h of y given x, irrespective of what p of x is, and we know if it is uniformly focusing, what is the maximum value of h of y, that is log of j, and it is the uniform input distribution that will result in that value of h of y. So, then for a strongly symmetric channel, we know what is the expression for channel capacity. So, for a strongly symmetric channel with k inputs and j output, the channel capacity is given by log of j plus summation of this pi log pi over all basically outputs, right. This we got from the property that strongly symmetric channel is uniformly dispersive. So, h of y is given by this expression minus of this expression. So, irrespective of what the input distribution is, and since the channel is also uniformly focusing, we know the max value of h of y is log of j, and it is the uniform input distribution that will result in that. Okay. So, this is the expression for this. So, we can use this to compute then, for example, capacity of this channel. What is the capacity of this channel? What is the j here? J is 2. So, log of 2 will be 1, and this is basically minus of binary entropy function of this small p, right. I have already mentioned it is the input distribution which is uniform that achieves capacity of a strongly symmetric channel. So, we know the expression for capacity of a strongly symmetric channel. Now, let us look at this channel. This was uniformly dispersive, right, but it is not uniformly focusing. We will show you this falls under what is known as class of symmetric channel. So, we can essentially partition this channel into strongly symmetric channel, and we will use the expression for strongly symmetric channel to compute capacity of these channels. So, we say a discrete memoryless channel is symmetric if it can be decomposed into L strongly symmetric channels with selection probabilities given by Q1, Q2, Q3, QL. Okay. Now, at this point, let us look at both these channels and just convince ourselves that these channels are both same. So let's look at input 0 to output 0. This transition probability is 1 minus delta. If you look here also, from 0 to 0, it is 1 minus delta times 1. It's the same. If you look from 0 to delta, transition probability is delta. So 0 to delta, this is delta times 1. Now if you look from 1 to delta, this transition probability is delta. So from 1 to delta, this is delta times 1, same. So 1 to 1 is 1 minus delta. So this is 1 to 1, this is 1 minus delta into 1. So both these channels are same. Now if you look at, this is one channel, let's say, and this is another channel, and you can see that I am selecting this channel with probability q1, and I am selecting this channel with probability q2. And what are these channels? Look at this channel. Is this a uniformly dispersive channel? It is, right? It is a uniformly dispersive channel. Is it a uniformly focusing channel? I am talking about this channel. Is it a uniformly focusing channel? It is, right? So this channel is a strongly symmetric channel. Do you know the capacity of this channel? This will be 1. Now what about this channel? Is this uniformly dispersive channel? Transition probabilities leaving this particular input is only 1, here also 1. So it's uniformly dispersive. There is only one output, so it has to be focusing also. So this is strongly symmetric channel. What's the capacity of this channel? Log of 1 is 0, and then this probability of 1, so it's 0. Capacity of this channel is 0, right? So if you look at this particular channel, think about it, it has been decomposed into two strongly symmetric channels. One is this one, another is this one, and we are selecting this channel with probability q1, which is 1 minus delta, and we are selecting this channel with probability q2. Okay, and I can write the capacity of this, because I know the capacity of these strongly symmetric channel. I can write the capacity in terms of capacity of these channels as well as selection probabilities, and this is what we are going to talk about now. How can we identify a symmetric channel? If the channel is symmetric, then how do we partition them into strongly symmetric channel? Like, given this channel, we first have to identify whether it's a symmetric channel or not. If it is a symmetric channel, how do we partition this into this? And then how do we compute the capacity, knowing that we know the capacity of the strongly symmetric channel? Can we write the capacity of this channel, symmetric channel, in terms of capacity C1, C2 and Q1, Q2? Can we write that? This is what we are going to talk about now. Okay. So I am going to talk about an algorithm to see basically whether a particular channel is symmetric or not. First step, partition the output alphabets into subset B1, B2, BL such that two output letters are in the same subset if and only if they have the same focusing. We know the overall channel is not strongly symmetric, but we are trying to partition the outputs in such a way that the outputs which have the same focusing, they are put in same set. Okay. So if you go back and look here, this one, so if you look at the transition probability is 1 minus delta, this is 1 minus delta, and this is delta delta. So which are the ones which have same focusing? 0 and 1. So, we club them together in one subset, and this delta has different focusing, that is in the different set. Okay. That is our first step. So, we are partitioning the output letter into subset B1, B2, BL, such that two output letters which have the same focusing, they are kept in the same subset. Now, when we are doing this, we have to basically ensuring that all the outputs are in some set, right, and the union of all these sets should be our overall all the number of basically output alphabets. Now, we need to check if all inputs have same dispersion into the subset Bi. If yes, then Qi is equal to sum of probabilities into Bi from any input letter. So, once we have partitioned our output alphabets based on the focusing, same focusing, now we need to look at each set and see if from each of the input there is same dispersion to that particular subset. So, I have a subset B1, I have to look at all the input and see if the transition to that particular subset B1 from all inputs when they are arranged in the descending order, if they are same or not. So, if you go back and see, so I clubbed 0 and 1, right. Now, I need to look what are the inputs, inputs are 0 and 1. So, I need to see what is the dispersion from 0 input to this set, which is consists of output letters 0 and 1. So, from input 0 I can reach 0 by basically 1 minus delta, and obviously I cannot reach 1 here. So, the dispersion from here to this particular set is 1 minus delta, and if you look from 1, dispersion to this set is basically 1 minus delta. You can reach 1 from 1 by 1 minus delta, and of course, you cannot reach 0. So, if we look dispersion to this particular set B1 from any input, whether it is 0 or 1, the probability is 1 minus delta and 0. So, that is same whether it is input 0 or input 1, correct. Similarly, look at this particular output from 0, this transition probability is to reach this is delta, from 1 it is delta. So, we can see that dispersion to both these set B1 and B2 from inputs is same. So, the second criteria is also satisfied. Is this clear? So, once you partition the output alphabets based on the same focusing, you look how are you, what is the transition from the input to that particular output alphabet set, and when you arrange those transition probabilities in the descending order, they should be same no matter what your input is. So, in this case we saw that they indeed have the same dispersion. If they have the same dispersion, then set Qi to be equal to sum of probabilities into Bi from any input letter. So, in this case, if you see for this set, the probability was 1 minus delta. So, we put Q1 as 1 minus delta, and for this set this probability was delta. So, we put Q2 as delta. Okay. Now, you keep on doing this for until all the output alphabets have been partitioned. So, if I equal to L, stop, the channel is symmetric and the selection probability Q1, Q2, QL have been found. If you have not reached I, then increment I and then repeat this. So, you need to do it until all the alphabets have been partitioned into this. So, B1 union B2 union BL should be the whole set B, and intersection between B1, B2, B3, BL is null set. Now, once you find out Q1, Q2, okay, once you have found out that these belong to one set and this belong to one set, now finding these probabilities is straightforward. Why? You know the original mapping from 0 to 0. You look at mapping between 0 to 0. You know Q1 is 1 minus delta. So, this into this should be this. So, you know this. Okay. So, like that you can find out these transitions. These transition probability you can find out, because you have now QIs have been found out. Now, you look at the original channel and this channel which has been partitioned into strongly symmetric channel, and you, so looking at the outputs, input output basically at both these channels, you can find out, I can find out this, I can find out this, I can find out this, and I can find out this, correct. Now, once you find out this, and obviously I know the capacity of this channel and this channel, and I will come to how to compute capacity, but at this point I want to ask whether it is clear to you how to check whether a channel is symmetric. To repeat, you basically first club the output symbols based on the fact that they are uniformly focusing. So, you partition all the output alphabets. Now, you look whether the dispersion to each of these set from inputs is same. From all the input, the transition probabilities when arranged in descending order to B1, whether they are same no matter what my input is. That should hold for B2, B3, BL. If that is correct, then your channel is symmetric. You equate Q1 to be equal to sum of probabilities of all transitions going into that particular set, and this is how you are now able to find the selection probabilities. Now, you look at mapping of the input and output in your original channel and in this partition channel, use that to find out the missing transition probabilities. Okay. Now, I am going to find out, given that I am able to partition a symmetric channel into strongly symmetric channel, can I utilize the fact that I know the capacity of strongly symmetric channel? Can I make use of that to compute the capacity of a symmetric channel? And I am going to show you some result first, which would show that yes, if we are able, if the channel is symmetric, we can write its capacity in terms of strongly symmetric channel and this selection probability. So, we have a setup like this. We have the same input going to all. So, remember what we are doing is we are partitioning the output based on same focusing. So, you can look at it as I have L such channel, parallel channels in some sense, and it's the same input that is going to this channel 1, channel 2, channel 3, channel L, because I am partitioning the output, but the same input is going to channel 1, channel 2, channel 3, channel L. So, I have a situation like this. I have an input X. Now, I have my channel which has been partitioned into, let us say, strongly symmetric L channel, right. So, this input X is going to each of these channel, and the output Y1 is only those alphabets which have the same focusing, right, because I have partitioned my output based on same focusing. So, you can think of now with selection probability Qi, I am selecting channel I. I am selecting with probability Q1 channel 1. If you go back and see, with probability Q1 I am selecting this, with probability Q2 I am selecting this channel, right. What I am saying is, I have a, think about it, I have a random variable Z which is essentially deciding which channel to choose. So, channel 1, channel 2, channel 3, and that probability is basically given by Qi. with Q1 probability I am selecting this channel, with Q2 probability I am selecting channel. So, the selection of the basically which channel is chosen, that is decided by this Z, okay, and probability of this Zi is basically Qi. So, what will be my output depends on what channel is selected. So, I can write this decomposed channel in this particular way. So, I have a basically general discrete memoryless channel created by these L discrete memoryless channel, where selection probabilities of each of these discrete memoryless channel is given by Q1, Q2, QL, and these are the assumptions I am making. All channels have the same input. So, the input to A1, A2, A3 is basically AL is A. Second assumption is there is no overlap between set Bi and Bj, because I am clubbing all those output alphabets which have same focusing into one subset, right. And of course, the union of B1, B2, BL should be the overall output alphabet size. And how I select this channel Z, that is independent of what my input is, because this selection probability. So, as I said, basically this Z is essentially indicating, okay, whether I should select channel 1, channel 2, channel 3, and this probability is given by this Qi, and that is independent of what the input is. Probability of Zi is given by this. Now, the claim I am making is this, that mutual information between this channel X and Y, this can be written in terms of mutual information of these individual channels. The claim I am making is mutual information between X and Y can be written as product of selection probability of ith channel and mutual information between X and the output of the ith channel. This is the claim I am making. I am going to prove this result, and then I am going to use this result to come up with the capacity of this symmetric channel in terms of capacity of these individual discrete memoryless channel. Okay. Now, again just recall the this thing, X is my input, Y is my output, and Y1, Y2, YL are the outputs of each of these discrete memoryless channel, and Z is selecting which channel basically. Okay. Now, H of YZ can be written as H of Y plus Z of Y given H of Z given Y. This follows from chain rule, and this is H of Y. Why this is 0? Why knowing Y you know Z? If I tell you what the output is, you know which set it belongs to, so you know which channel has been chosen. You understand? Because Z is basically selecting basically, okay, this channel, that channel, right. If I tell you the output is, you know this output belongs to which set. Okay. So, there is no uncertainty in Z knowing Y. So, this will be 0. So, this is H of Y. Now, H of YZ can also be written as H of Z plus H of Y given Z. This follows from chain rule. Now, I equate this to this. So, H of Y is H of Z plus H of Y given Z. Now, H of Y given Z can be written as H of Y given Z is I multiplied by probability of Z being I, right, and I have L such channels, so I can write it like this, right. So, again this follows from the definition, right, you can write it this way. Now, what is the output Y when Z is I? I am denoting it by Yi. If you go back, basically, and see the output of first channel I am writing as y1, y superscript 2, y superscript. So, if ith channel is chosen, I am using the notation y superscript I. So, this I am writing in this particular way. Okay. Is it clear so far? Now, of course, Pzi is given by this. Now, let us compute this. H of yz given x. This can be written as h of y given x plus h of z given xy. Chain rule. And again, basically, uncertainty in z given xy. If you know y, there is no uncertainty in z. So, that is h of y given x. Now, this I can write as h of z given x plus h of y given x of z. This follows from chain rule. Now, h of z given x is h of z. Why? Because x and z are independent. So, this is h of z plus h of y given x z. Okay. Now, I equate this to this. So, I get this expression, and again I can write h of y given x z as h of y given x, and z is I multiplied by the probability of z being zi. So, this is uncertainty in yi given x multiplied by qi. So, this is h of y given x. We have already computed h of y. What is mutual information? H of y minus h of y given z. H of z is common. H of z is here. H of z is also here. Here we have summation h of yi given x into qi. There we have summation h of yi into qi. So, if we compute this, we get this. So, this can be written as mutual information between x and yi. So, I have shown you that mutual information between the input and output can be written in terms of mutual information between these decomposed channels and their selection probability. Okay. Now, let us look at how we can compute the capacity of this symmetric channel, given that we know what is the capacity of the strongly symmetric channel. So, this is the claim I am making for a symmetric discrete memoryless channel. Capacity is given by product of the individual capacity of this discrete memoryless channel multiplied by their selection probability, where Ci is the capacity of the strongly symmetric discrete memoryless channel and Qi is its selection probability. I also claim that it is the uniform input distribution that achieves capacity. So, we have just shown this, right. Now, capacity is maximizing this mutual information over all input distribution, right. Now, this can be written like this. This mutual information can be written in terms of this. Now, so I can write this as maximizing this over all input distribution. Now, I wrote this. This is less than equal to summation Qi max of mutual information between x and yi. Why did I put less than equal to? Yes. So why is that causing this? Jensen's equality, okay. You can use basically Jensen's equality. So basically the input distribution which maximizes this and input distribution which maximizes these individual channels may not be the same, right? So this is given by this. Now this can be written as, so this is maximizing this mutual information with x and yi. That's basically, yeah, we can as a, what is this mutual information as a function of p of x? That's a concave function, right? So basically we are, okay, so basically look at this, the input distribution that maximizes this input, this thing. Now what we are doing is, we are looking at input distribution that will maximize this individual capacity of this channel. Now this input distribution which maximizes, let's say, first channel may not be the same input distribution which maximizes the second channel, third channel, fourth channel. We have not yet proved it, right? So this will come out to be more than this input distribution which maximizes the overall channel. We will show that actually this is the same distribution which maximizes channel 1, channel 2, channel 3, but as of now we have not yet proved it. So here basically this is input distribution which is maximizing the input with channel 1. There might be a different input distribution which maximizes channel 2. So this can be basically greater than or equal to this. Now what I am saying, this I can write this as capacity of this individual channel. So what I have said here is C is less than or equal to Qi Ci summation over I. Now I am going to show you that the input distribution that maximizes the first channel is same as what channel maximizes the second channel, the third channel, the LH channel. So this is actually, so the distribution that maximizes this is same as the same distribution which maximizes individual channel, and that is why C will be equal to, not less than equal to this summation Qi Ci. Okay. Now our expression is satisfied with equality if and only if there is a input distribution which simultaneously maximizes mutual information between x and y1, x and y2 and x and y3, x and yn, correct. Now what are these individual channels? These are strongly symmetric channel. And what is the input distribution that maximizes the capacity of these strongly symmetric channel? Uniform input distribution. We have shown that it is the uniform input distribution that maximizes the capacity of maximizing mutual information, right. Its input distribution is, it is a uniform input distribution which achieves capacity for a strongly symmetric channel. And we have also seen it is the same input which is going to channel 1, channel 2, channel 3. So if let us say I have k input, the distribution that maximizes capacity of first channel is P of x given by 1 by k. It is the same distribution which maximizes the capacity of channel 2, channel 3, channel L. Okay. So since each of these channel is a strongly symmetric channel, it is the same input, and it is the same input going to the each of these channels. It is the same distribution which simultaneously maximizes each of these. Hence C is actually equal to summation Qi Ci. Okay. So what we have shown is, first we have shown how to find whether a channel is symmetric or not. If the channel is symmetric, we know a mechanism of decomposing it into strongly symmetric channel and finding out the selection probability. Now we are saying is, we can also compute the capacity of such symmetric channel in terms of their selection probability and capacity of the strongly symmetric channel, which we know, and that is the result. So, let us look at a very simple example. This is a binary erasure channel, the example that we were doing. So, we had 2 inputs 0 and 1, and we had 3 output. So, this was a channel was like this, right. Now, this is not a strongly symmetric channel, because we can see 0 and 1 have same focusing, but delta has a different focusing. So, it is not a strongly symmetric channel. So, let us see whether we can decompose it into a strongly symmetric channel. We have already seen that we could club 0 and 1 in one set, and we can put delta in other set, and we already did this. Basically, we computed selection probability, right. So, this was the decomposed channel. Now, we know the capacity of this channel, that is 1, we know the capacity of this, that is 0, we know the selection probability, this is Q1, this is Q2. So, we can now compute the overall capacity, which is basically Q1 times C1, 1 minus delta, and C2 is 0. So, the capacity of this channel comes out to be 1 minus delta. So, that is basically the capacity. In general, basically finding capacity of channel is not a very simple problem. In some of the other channels, I mean simple channels, you could try to write, for example, because you are trying to find an input distribution that maximizing capacity, you can try to write the expression for mutual information in terms of transition probabilities and input distribution, and try to, let us say in case of there are only 2 inputs, you can take probability of 0 being p and other as 1 minus p, and try to write the expression for mutual information in terms of one parameter, and try to find what is that parameter that will maximize capacity. So, you can do that. In general, finding capacity of a channel is not. There are also algorithms to compute channel capacity and things like that. We are not going to go into this, something called Blehut-Erumoto algorithm for finding rate distortion function and channel capacity. We are not going to cover it in this course. So, I will conclude.